So thank you for being here on the first morning for the first talk. So I'm going to talk about what I call difference dice. I'm from St. Peter's University, just on the Jersey side of Manhattan, but let me also mention that I'm the editor of the College Mathematics Journal because we have an annual puzzles and games issue in September, and we also publish other recreational mathematics during the year. So as you have things come to fruition that you might want to have published, please think of us as a place that might go. So this is in addition to all the other anniversaries. Is not moving. Okay, we'll do it that way. This is the 40th anniversary of Sicherman dice. Who's heard of those before? Sicherman dice? So for those of you who haven't, in 1978, Martin Gardner presented the idea of Colonel George Sicherman to label dice in a slightly different way. Rather than having two dice labeled 1, 2, 3, 4, 5, 6, one is going to be labeled 1, 2, 2, 3, 3, 4, and the other is 1, 3, 4, 5, 6, 8. But what's the point of that? If we look at the table of these two dice, on the left-hand side, you have 1, 2, 3, 4, 5, 6 against itself. This is what is in every probability book about finding probabilities for sums of two dice. On the right-hand side are the other ones. This Sicherman dice, 1, 2, 2, 3, 3, 4 versus 1, 3, 4, 5, 6. And you see the table inside there is not nearly as nicely structured as the one on the left, but they do both have 1, 2. And this is going to be slow because of the way this is happening. But the nice thing about starting first is there's no bar for special effects. So both of them have 2 3s. Both of them have 3 4s. I'll just keep scrolling. They have 4 5s, 5 6s, 6 7s, 5 8s. This is the only time we have to go through this. 4 9s, 3 10s, 2 11s, and 1 12. So what that means is that in terms of the sums and the frequencies of the sums, these two pair of dice are identical. If you could only see the sums for some reason, you couldn't distinguish between the two of them. So you might wonder, how does one find these things? You can do it by brute force. It's actually a nice classroom activity for those of you who teach. And of course, you start not by saying, find it. You say, is there such a thing? And often it's when the students are trying to prove there's no such thing that they actually find it. The nice approach for this, though, is using some algebra. So I can encode the two dice, and I'm going to put the labels in as the exponents. And then when I square it, the coefficients you see are going to give me the frequencies of the sums. So this is a first example of generating functions, or something I've heard also called enumerators. So then to find the Sicherman dice, we are going to do what we've done since high school algebra. We're going to factor things. I'm going to factor that into irreducible components, and then recombine them in a different way. And you see what I end up with at the end is a single 1, 2 2s, 2 3s, and a 4, and then a 1, 3, 4, 5, 6, 8. And if you have some conditions on what it means for polynomials to correspond to dice, you can convince yourself that the Sicherman dice are the only other possibility. So now, well, what if we change the operation? What if we look at difference dice instead? So this is where I've gone high-tech in a different way with different colors. If you look at two normal dice and you look not at their sums but their differences, and since the dice are indistinguishable, we'll say that's either the absolute value of the difference, or always just take the largest die minus the smaller one. There's 6 zeros, 10 1s, 2 8s, 6 3s, 4 4s, and 2 5s. So are there others? Well, we can do the same algebra. We won't look at this carefully at all, but it's the same approach we used before to find the Sicherman dice. And that leads to that thing on the right. 1, 3, 4, 5, 6, 8, that was the same. And then the other die is 3, 4, 4, 5, 5, 6. And lo and behold, it has the same distribution. So you think, okay, well, the algebra gave me a unique solution there, so I must be done. But what happens is that there are others. So here's a whole different set, a 2 more pair, where things work out to be just the same way. 1, 3, 4, 5, 6, 8 now versus 3, 3, 4, 4, 4, 5. Or on the right-hand side, the normal 1, 2, 3, 4, 5, 6 versus 1, 2, 2, 3, 3, 6. And both of those work out. And there are actually dozens and dozens more of these. So how did the algebra fail us? Why are these things happening when we thought the algebraic technique was unique? So what's going on is that factoring towards the top polynomial there, so that first expression corresponds to the first two pair of die, the 1 through 6, and then the Sicherman-ish die for the difference. And you see that it's balanced. So for instance, I have a 3x to the minus 3 term and a 3x to the positive 3 term. But if I'm looking at absolute value, that's really too restrictive. The third pair corresponds to this one. The fourth pair corresponds to this one. The colors I've highlighted, you see there are both two things in all of them that have an exponent of -5 or 5. There are 8 things in all of them that have an exponent of -2 or 2. Thank you. So how did the algebra lead us astray? Well, what I need to do, if I'm going to think about absolute value, is put these together and think about a to the -k and b to the k, combine those to be a plus b to, I'll put x to the plus minus k. So all those things correspond to this expression down here. 6 zeros, 10 plus or minus 1s, 8 plus or minus 2s, 6 plus or minus 3s, 4 plus or minus 4s, and 2 plus or minus 5. So my ending note is not a big conclusion or anything, it's a big question. What are the mathematical tools or methods that can allow us to find all the combinations that correspond to an expression like that? Or a little bit more pithily, how can you factor such an expression? I'd love to know. This is small enough you could do it with a computer, but in general, you'd like to have a better technique. And if you have any ideas, I'd love to hear them. Thanks for your attention.